So our next speaker is he's going to talk about the challenges for an axion explanation of the muon minus 2 measurement. Okay, please.
Thank you. Thank you everyone for staying. So my name is Chen Sun. I'm a postdoc at Tel Aviv University, and this is recent work that I collaborated with Mamal Bouambad and Gigi Pham from Brown University and Matt Rees from Harvard. So I believe all of you have heard that the recent Fermilab result combined with Brookhaven result on this muon anomalous magnetic moment is bigger than the standard model prediction. And an interesting question I believe a lot of you have asked is whether that implies some sort of beyond standard model physics that could explain this anomaly. So here are some very general rules if we want to invoke new physics to explain this muon G-2. And the first one is that we want to suppress the electron G-2. Right, because the experimental result is quite compatible with the standard model prediction. And on top of that, we want to suppress the CP violation in general, because otherwise the model would be heavily constrained by the electric dipole moment constraints. The third constraint comes from the flavor violating process. So in principle, we also want to suppress the dangerous operator that causes the flavor violating process. And from a theoretical point of view, if we want to extend the standard model, we have quite a few choices. We could, in principle, go with the new scalars and new vectors, which could cause some problem of the naturalness to make it worse, unless they are embedded in a bigger theory like SUSY. Or we could turn to new fermions or new Nabucco-Sun bosons, which makes the axion a very appealing candidate if they could address the muon G-2 anomaly. And now let me just very quickly go through this axion effective field theory just to underline the viable parameter space if we use it to address the muon G-2. So here is a generic Lagrangian between the axion and the standard model content. We write down the coupling between the axion and the fermion, and also the axion and the photon. They correspond to the blue dot and the red dot in these three diagrams. And the size of each diagram is estimated and written below. We have now two simplified scenarios for benchmarks. Of course, we could have axion coupled to both muon and electron and photon. Now, but let's look at two cases. One is that the axion couples muon and photon. The other is axion couples to muon and electron. In the first case, in these two plots I'm showing, in both plots, the x-axis is the axion-muon coupling, the y-axis is the axion-photon coupling. The only difference between these two plots is that the axion mass is chosen to be different for different benchmarks. And the band corresponds to the parameter region where the muon G-2 could be explained by these operators. And immediately you notice that they require this axion decay constant, or in other words, the axion coupling to photon and to muon to be fairly large. In general, they need to be larger than roughly 100 GeV inverse. Okay. And to show you the existing bands, this is so the shaded regions, they are the existing bands, and the transparent blue band is the one with the that explains the muon G-2. We derive this blue band by minimizing the required axion-photon coupling and vary this axion-muon coupling. When the axion-photon coupling is minimized, the corresponding axion-muon coupling is shown in this plot on page 7, and you can see that this transparent blue band is below the existing, the Babar constraints. Okay, so This is the case for the axion that coupling to muon and the photon. Now on this page I'm showing is the axion coupled to muon and electron. Similarly, in these two plots, the only difference is that we choose different axion mass, 1 GeV versus 5 GeV, and the axis is muon axion coupling. The y-axis, again, instead of axion photon coupling, we have the axion electron coupling. So the red band is the parameter region where the muon G-2 could be explained, and this blue or purple region is the region where the electron G-2 is compatible with the existing result. And in this case, again, we need the axion coupling to muon and electron to be rather large. They are as large as 100 GeV inverse and above. And at its face value, this effective field theory tells us that we could find parameter region where this axion can address the muon G-2. But is it really true? Is this the whole story? Of course not. We need to complete the model. And once we complete the model, we realize there are actually more challenges for this sort of solution. And we have now two choices. We are faced with either allowing muon to be charged under the PQ symmetry or the muon being neutral, but it couples to some other fields that are charged under U1 PQ. So let's first look at the choice 1. In this case, we can have a few different complex scalars, and all of them break PQ. A subset of the scalars, they break the electroweak scale, electroweak symmetry, and phi in our notation is the PQ scalar that spontaneously only breaks PQ. Okay, and immediately you notice that there is a big difference compared to the usual axion, what we call the invisible axion. In those cases, what we want is to raise the decay constant to be way above the electroweak scale, and that can be easily achieved by having a large valve for this PQ scalar phi. But in our case, we want the small decay constant that's even below the electroweak scale. And that can be achieved if we arrange some hierarchy between the valves of different scalars. So in our case, we want the valve of one scalar to be larger than the rest, so that the component that's eaten by z is dominantly from the phase of this scalar. And the axion is a linear combination of the phase of the scalars that have a smaller valve. Okay. And in that case, we could have a decay constant that's below the electroweak scale. And this is our field content. We have three complex scalars, and we have up quark, down quark, and lepton. And in our scalar potential, we start with 3 copies of U1s, U1 cross U1 cross U1, and we explicitly break it to U1 cross U1. And this is quite similar to the DFSZ type of construction. And our HQ couples only to quarks, and our HL couples only to leptons. And all that's left is quite straightforward. All we need to do is to identify the axion mode, the specific direction in the phase that is our axion. And that can be done by first identifying the part that's eaten by z. As I promised, you can see that in this linear combination, the phase that comes from HQ, the scalar that couples to quarks, is dominantly eaten by z because of the hierarchy between the valves. And because we start with 3 copies of U1s and we explicitly break it, now a component becomes massive, and that is the component related to this explicit breaking term. And now we only have one linearly independent direction, that is our axion field. And in this expression, you can see that this dominantly the linear combination of the phases that comes from the PQ scalar and the scalar that couples to leptons. Okay. And finally, we can write out the coupling between the axion and lepton. And again, you can see that the axion quark coupling is suppressed, and also the axion photon coupling. From this, we can make a few observations. We have the indeed the axion decay constant to be smaller than the electroweak scale, and there's no axion gluon coupling. And also, very importantly, we have this axion muon coupling that has the opposite sign as the axion photon coupling. That's important because only if they have the opposite sign, the contribution to the muon G-2 is in the right direction to raise the standard model prediction instead of lowering it. But we also have a few more observations that we actually didn't want. For starters, we have this the Webb hierarchy tells us that there could be light charged Higgs, but those are very constrained by lab. And in order to reproduce the standard model light couplings, we need the alignment limit, but that is hard when extra Higgses are so light. Also, we have the radial mode of phi that could cause the exotic decay of the standard model Higgs. And very importantly, because now we complete the model and the X-ray ingredients are not that heavy, that leads to the direct contribution from the X-ray ingredient, and they directly contribute to the muon G-2. Okay, so these are the challenges in this sort of construction. And of course, there are dedicated studies on 2 Higgs doublet models and also the global electroweak fit on these 2 Higgs doublet models that I'm not going to go over with details. And the other choice, as I mentioned, is that muon could be neutral under U1PQ, but they could mass mix with something that is charged under PQ. So here's the recipe. I'm going to go through it real quick. We start with something. We start with the lepton that's not charged to U1PQ, and then we introduce some vector like fermion that is charged under PQ. Of course, we still need the PQ scalar, that is our phi, and we want our lepton to mass mix with the vector fermion. This can be done using these terms we write here, and when this mass mixing is smaller than the vector-like fermion, the vector-like fermion can be integrated out, and that leads to the derivative coupling between the axion and our lepton. Okay. And here's the almost the last page, and we can see that in this model we don't have the axion photon coupling, and also our axion electron coupling and axion muon coupling, they have the same sign. That is a small problem, not a big one, because that can be fixed if our extra vector-like fermion has different PQ charges. A more serious problem is that if that implies light charged fermions, and that could lead to decays that are heavily constrained at collider. And again, like the first model completion I demonstrated, we also have a challenge that's related to the direct contribution to the muon G-2 from this extra ingredient. Okay, just to quickly summarize, axions are benign candidates that are for light modes, and from the purely effective field theory point of view, axion could almost address this muon G-2. Yet when we try to complete the model, we immediately realize that because we need a fairly large coupling between the axion and either muon or electron or photon, and that always gives us some charged modes, either charged fermions or charged scalars, or neutral modes that are very light, that causes the exotic decay of standard model Higgs. And of course, because these extra ingredients are low scale, they contribute to the muon G-2, which sort of defeats the purpose of using effective field theory from the first place. And those are the challenges from the exercise. Thank you.